In the previous video, we went over how to use load and store instructions with the base address and modified base address. And then I mentioned that we can actually update the base address kind of automatically. So in case we have a loop or whatnot, we don't have to go and manually keep incrementing the numbers. So there is a principle in ARM language that is the pre-index and post-index addressing. So what we've done so far is what is called pre-indexed, meaning if you have a base address, you load from that address. If you have an offset, you calculate the offset before you perform your load or store, whether that is register offset, immediate offset, register scaled offset. We calculated the base address plus some value, and then that was our quote unquote new address or the address that we're dealing with. And we either loaded or stored to that location. So another thing we can do is something called the actually this is the pre-index, and we can add the exclamation point at the end of our instruction, and that will actually update the base address after the instruction has executed. And this is typically referred to as pre-indexed addressing. And essentially, once the instruction finished executing, whatever the offset that you added to the base address, together with the base address will become your new address. So let's see how this affects our code in the previous example. Okay, so I'm going to execute the code one step at a time. Again, I have a pointer pointing to the same alphabet, nothing changed there. And I'm going to load a word from that location, store it into R1. And in the next example, I'm going to load a word from the base address +4 and store it into R2. That's my new value. Now, notice the difference here is that my R0 has been updated. It's updated to whatever the old address was, the base address, +4. So now it contains the old address +4, which is 10000004. And if I move my, or if I execute the next instruction, I have 8 loaded into R4. And then I'm going to load. Now, again, the difference now, my base address now is the 104. I'm just going to say 04, okay, as a shortcut for the whole number. So it's 04. It was 0. Now it's 04. So I'm going to add 8 to that 04. Now I'm actually loading from location 12 into R3. So R3 contains 6, so 706F, 6E, 6D. If I go to memory, I go there and I go to address. We said, what was it? Address 12. So this will be 0C. Right. So it is loading from address 12, which is the 706F, 6E, 6D. If you remember previously, without having that exclamation point here, the base address did not change. And when we offsetted that by 8, we loaded from address 8, we loaded actually this word into register R3. So the same thing will happen with the logical shift left or the register scale offset. Once I calculate the new address, I will store it back into, actually before I go to that instruction. So now my new address was at address 12, and now 12 will be stored into R0, and that's, or 12 plus a base address. So that's 100000C. That's my 12. And I've noticed that actually was stored into R0. And if I do the same thing with the register scaled offset, I'm going to load a word from that location. It's the base address. In this case, it became 12 plus 16. And I'm going to move that value into R5. And that's actually outside the alphabet. So this was 12 plus 16. It will put me on this block right here, and I'm moving the 0 into R5, and that's why I got the zeros here. And the same thing goes for the register for the store instructions. So I can actually, it doesn't make sense when you do an update. Let me they do the same thing. You're loading a value from that location, from this register, storing it into that location. I'm updating the address anyway, but there's no offset, so the new value will be the same as the old value. There's no offset there. And then the next one, I'm going to store the value from R2. R2 contains 68, 67, 66, and 65. I'm going to store it into that location. And then I'm going to update the content of R0 to be pointing to the new address. And the new address is R0 contains 1C, 1C plus 4. So if I execute this, 1C plus 4, C is 12, so 4 will make it 16. So it went from 1C to 20 in hex. Is right there. Okay, so what you have seen here so far is called the pre-index. Like I said, in summary, what happens is you calculate the address. So two properties of pre-index. Let's write them here. Two properties. First, you calculate the new address, and then you perform, or then the assembler performs the operation. So whether load or store. And then the other thing is you have the option to update the base address. Okay, so calculate the new address. We've done this before without using these exclamation points. We calculated the new address, the effective address, and we loaded a value from that into our register, or stored a value from the register into that location. And then we had the option to update the base address. And to do that, we simply just add this exclamation point. And this essentially will update the pointer to the new address. Now, there is another way to do this load and store with something that is called post index. So post indexed addressing. I'm going to do similar examples. So we're going to load, sorry, we're going to make the pointer point to the alphabet. We're going to start from the beginning. And I'm going to load a value into R1 from where that pointer is pointing to. You guys have been familiar with this so far. But now I'm going to actually put the immediate value outside the bracket. So you see here that previously what we did is we put comma hashtag 4 to increment the base address by 4. But in this case, I'm actually putting the hashtag 4 outside of the bracket. And that essentially is going to perform the operation on this address and then update the base address of the pointer with the new value, which is the base address plus 4. So in pre-indexing, you calculate the new address and then you perform the operation. In the post-index, you perform the operation and then you update the base address. And notice here, I don't have this, I cannot put this exclamation point. It will always update the base address with the new value. So let me write some instructions here and I'll show you what they do in a second. So again, let's say this is the base address and oops, R0. And we still have R4 unchanged, so I have R4. And I'm going to load R3. We can do again 0 with 4 and LSL. Let's do hashtag 1. Now, just my worry is that we're incrementing the address after each operation, and then we're going to get to a point where we're actually getting way out of range where this alphabet is stored. But again, I'm just really focusing on the fact that we'll just take a look at the content of R0 and these registers. And then you can do the store the same way. You can do, well, let's do these first, and then we'll see what goes on. Okay, so I'm going to run the code down to the post indexed. And now we'll see how this will differ. Okay, so now R0 is pointing to the alphabet. Alphabet is stored starting at that address. Now I'm going to load a word from that address, from the base address, and then increment the pointer by 4. So I should see that word loaded into R1, and then the value of R0 to be 10000004, which is true. So again, there's no change in R1 because it's this. I'm still loading the same word. It just happened to be now the address is automatically updated. I did not need to put that exclamation point. This is scaled register, or this is just a register offset, and I'm going to now notice that my R0 is pointing to address 10000004, and I'm going to load from that address. So I'm going to load the next set of characters, and then I'm going to add 8 into that address because R4 still contains 8. So R0 should be C, right? So now R0 has been updated to contain 10000000C, and I still loaded the same stuff from before. It just happens that, again, the address has been updated after I loaded the word from the memory. And then the same thing goes for register scaled offset. Okay, so far you learned how we can make a pointer to some location, load a word or store a word to that location. We learned how to do offsets. We learned how to do pre-indexed and post-indexed addressing. And just for comparison purposes, I'm going to show you the difference if and when we do post and pre-indexing. So I'm going to show you something here real quick. So this is just a comparison. I'm going to, again, reinitialize the pointer to point back to that alphabet location. And I'm going to use an LDR and do R, let's make this R2 and this is R1. And I'm going to load from that location +4, right? And I'm going to show you the difference of what will be loaded into R1 and R2. So just running this code here, compiling, and then I'm going to load it. Okay, so let's run it down to here. So R0 is going to point to the alphabet. Alphabet is stored at that location. The first time I'm going to go to that location and load a word from that address +4. So if I go back, let's go to that location. So this is the base address. The base address +4 will be this value, 65, 66, 67, and 68. So if I perform this instruction, this is my 65, 66, 67, and 68 stored into R1. And the base address has not been changed. The pointer, sorry, has not been updated. And then if I execute the next instruction and store that into R2, now I actually first loaded from that location. I loaded from the base address, and then I updated it by 4. So first I loaded the value from that address, 61, 62, 63, 64, and then I updated the pointer by 4. Okay, so that's a different. Now you see we have two different values being loaded into R1 and R2. When you do post indexing, you calculate the address and then you perform the operation, whether a load or store. And if you're doing this is pre-indexing, and if you're doing post-indexing, you load or store first, and then you update the pointer at the end. And again, you have the option to do this here as well. The exclamation point. You can do that like this, but that's optional. For post-indexing, it always updates the base address. Now, to just put it all together, you can also do the same thing for bytes, actually. So you can change those into load a byte, for instance. And I don't necessarily need to increment by 4. I can just increment by 1 because I'm loading a byte, and a byte takes one address. So increment the pointer by 1. And this will still do the same. The principle is still the same. Post index, pre index are still the same. And when you do store, you can do the same thing. All these instructions are, or all these variations are applicable to the store. You can do a post index storage, pre index storage. You can store a byte, store a byte, store a word, half a word as a pre or post index, just like we're doing down here. So this is compiled, downloaded to the board. I'm going to run the code down to the alphabet, and then I'm going to grab a byte from that location, store it into R0. If I execute this, first byte I have is 62. And if I, well, actually it's a B, right? Because the first byte contains a value of A, which was 61, and the next byte contains B, and B is 62. But notice the pointer has not been updated. And on the other hand, if I do the second instruction, this will go to this base address, and it's going to load the value from that address, which is an A. A is 61 in hex. It will put it in R2, and then it will update the pointer by 1, and my pointer now points to this location, 1000 0001. Thank you for watching, and I'll see you next time.